Very good morning, dear student friends. Welcome you to the topic on EV charging system of the course titled Smart Grid Basics to Advanced Technologies. The EV charging infrastructure, as you could see, which has been taken out of the source available at Niti Aayog, and most likely, as you could see, there are two different type of charging concept. One is from AC, the other is DC, and the e-vehicles or so-called e-mobility expected to be one of the serious loading to our electric network in future. As of now, the four-wheelers of e-mobility, though it has shown its presence in this country, but it is not so significant. However, the three-wheelers are almost reached more than 2.5 to 3 crores as of now. So, country like ours, electric vehicles, especially two-wheelers, three-wheelers and four-wheelers are going to play a major role as well as a concern to Indian power system in future. Electric vehicles are always charged with DC. If the input is AC, then a conversion stage is required to convert AC to DC. And mostly it is from AC to DC because of residential charging or parking systems. There are four modes of EV charging operation. The mode 1 consists of a direct connection from a socket to the EV without any special safety. Typically, mode 1 is used for charging electric bikes and scooters. The mode 2 of charging scheme requires a specific safety system between the point of connection to the electric network and the car in charge. The system is placed on the charging cable and is called the control box. It is installed on portable chargers of electric vehicles. This can be used in public as well as in domestic sockets. The next mode of operation, mode 3, requires an EV-SE equipment to charge the electric vehicles, which is permanently connected to the electrical network. Moreover, the control box is inherently integrated into the EV-SE. Wall boxes, commercial charging points and all automatic charging system comes under this mode of charging. Mode 4 offers DC supply directly to the electric vehicles. This requires a current converter external to the vehicle that connects the charging cable. In the figure, we can observe the AC charging modes are all on the left side to you and the DC on the right side with the socket pins. The AC charger ranges from 2 kilowatt to 22 kilowatts and the DC chargers range from 2 kilowatt to more than 200 kilowatts. Now you can see different models of DC charging plugs from Tesla and many other manufacturers. USA and Japan have type 1 AC and type 4 CHAdeMO DC, combo 1 AC DC and Tesla's proprietary AC connector. Europe has type 2 AC, type 3 AC, type 4 CHAdeMO DC and combo 2 AC DC. China has type 2 based AC and its own DC GBT connector. With respect to car manufacturers, Americans, Europeans, Koreans car manufacturers have adopted CCS combo and Japanese car manufacturers have adopted CHAdeMO. As the number of EVs is growing day by day, the adoption of new technology has seen exponentially growth. Hence, the stated charging connector list is indicative and will get changed over a period of time. Now, the architecture of EV charging system, where you could see there are multi-stage charging mechanism for electric vehicles. The architecture followed in India is EV connected to EVSE, which is monitored by CMS by user application. EVSE, electric vehicle supply equipment, which connects the charger to the main electrical supply. It also offers authentication, metering, payment services and remote monitoring. Bureau of Indian Standard BIS has published standards IS 17017 that covers the general requirements and safety norms for EVSEs. Charging protocol defines the type of connector that goes into the vehicle inlet, max power and voltage for connection, communication protocol and the type of communication links. Now, next is CMS, which is Central Management System, is a cloud-based platform managed by the company operating the charging station. The EVSE communicate with the CMS to manage the user authentication or authorization, billing and rate of charging. It also enables user-defined apps to help end users to identify the nearest charging station and also reserve a charging slot and pay. Now, the smart charging concept for optimal electric vehicle integration and its advantage of smart charging. For utility distribution network operators, it helps in more hosting capacity, faster implementation and less cost. For utility transmission system operators, it extends the limitation in system peak load and avoids the construction of additional generation capacities. For building managers, time of use tariff optimization, PV balancing optimization, demand charge management and demand limitation, load balancing and reduction of the connection fee. Now, considering the EV charging system in this country, because the manufacturers are many, so it is equally important to have EV charging standards. Now, you can see different elements and their standard type and components of different EV charging equipments or devices. This slide presents the essential charging components and their standards. The charging interface, which includes plugs, sockets, vehicle couplers, follows IEC 62196-1/2/3. The communication protocol, that is V2G/data link layer and physical signaling process, ISO 15118-1/2/3 and ISO 11898-2. The EV conductive system follow IEC 61851-1/21/22/23/24. The battery swapping follow IEC 62840. The conductive charging connection set poses GB/T 20234-1/2/3. China and the information technology safety equipments have IEC 60950-1. In our laboratory, we have a DC fast charger type 2 which is VEVC001. Generally, the DC fast charger with high power operation, the AC-DC converter, DC-DC converter and the power control circuits become larger and more expensive to keep in an onboard charger. This necessitates the implementation of an off-board charger so that it does not take up space within the vehicle, and the DC fast chargers can also be shared by many users. As we can see in the schematic, the input voltage is 415 volt AC supply. In the first step, the alternating current or AC power provided by the AC grid is converted into direct current or DC power using a rectifier inside the DC charging station. Then the power control unit appropriately adjusts the voltage and current of the DC-DC converter inside the charging station to control the variable DC power delivered to charge the battery. There are safety interlock and protection circuits used to de-energize the EB connector and to stop the charging process whenever there is a fault condition or an improper connection between the EB and the charger. The battery management system or BMS plays the key role of communicating with the charging station to control the voltage and current delivered to the battery and to operate the protection circuit in case of an unsafe situation. So, this is the input coming from 3-phase AC supply, which is a 5-wire system with 3 phases, including 1 neutral and 1 ground. This is the auxiliary battery system to operate the components in the charger. We can see that it is guarded by an MCB. From the MCB, it proceeds to the power conversion system, that is rectification and DC-DC conversion. This is the control unit that controls the charging and communicate with the BMS whenever any fault in charging. The control unit send the signal to the BMS to cease the charging process completely. This EV charger works on GB/T 20234.3 protocol BVC001 model. The rated input current is 25 ampere. The output voltage is 48/60/72 volt DC and 200 ampere maximum, and the load capacity is 15 kilowatt maximum. Now, the issues related to fast charging. Fast charging is quite attractive in the sense of high power charging with short duration of time or short charging times. But the fast charging power cannot be increased infinitely. That is due to 5 technical limitations. First one, higher charging current leads to higher overall losses both in the charger as well as in the battery. As the charging current increases, the effective capacity of the battery decreases as well. For example, as given in the Peukert's law. The second one, the battery C rate increases with fast charging, and this reduces the battery lifetime due to the heat produced and increased degradation due to the higher temperature. Point number 3, when fast charging takes place within a battery, the SOC of the battery can only be reached till 70 to 80% and maybe little bit more like 85 to 90%. But this is because fast charging create a lag between the voltage and state of charge SOC, and this phenomena increases as the battery is being charged faster. Hence, fast charging is typically done in the constant current or CC region of the battery charging, and after that the charging power is reduced in the constant voltage or CV charging, that is the constant voltage charging. For any EV charger, it is important that the cable is flexible and lightweight, and for people to use and connect it to the car. With higher charging power, thicker cables are needed to allow more charging current. It is very simple. I mean, if you like to, the resistance which decides your diameter of the conductor, and based on the required power, if you like to push maximum, then probably the size of the cable need to be increased. Else it will heat up due to the losses. In the future, with currents above 250 ampere, the charging cable should become heavy and less flexible, because they are so thick, so you perhaps cannot fold it as you wish as so, and it is not comfortable to use at all. The solution would be to use thinner cables with cooling and thermal management to ensure that cables do not heat up quickly. That is, of course, more complex and costly than using a cable without cooling system. Now, coming to an end, to conclude in this lecture, we have learned that different types of EV charging systems available, different standards for electric vehicle charging, and its architecture followed in India based on different manufacturers across the globe. A practical demo of the components involved, its architecture and working of EV charging system is also being understood in its basic form. I hope this lecture has brushed the basics of EV charging systems, but once again I request all of you to read more literature to understand more about electric vehicle charging mechanism for better understanding. Thank you very much.